Structural, dielectric, and electrical properties of Lead-freeNa0.5Bi0.5Ti0.9Zr0.1O3 Abstract ceramic samples of zirconium substituted sodium bismuth barium titanate of composition Na0.5Bi0.5Ti0.9Zr0.1O3 a polycrystalline orthorhombic compound have been synthesized by conventional solid-state reaction method at high temperature, i.e., at 900 degrees Celsius. The impact of Zr.1 on the structural and microstructural properties of Na0.5Bi0.5Ti0.9Zr0.1O3 was explored by XRD and SEM. The room temperature X-ray diffraction study guaranteed the advancement of single-stage compound with orthorhombic structure. The dielectric examination of Na0.5Bi0.5Ti0.9Zr0.1O3 explored over an expansive frequency extend, Hz, at different temperatures, 100 degrees Celsius, 500 degrees Celsius, showed that the dielectric properties of the material are reliant on both frequency and temperature. Dielectric study uncovers that the ferro to paraelectric stage change of the studied compound is a temperature of 300 degrees Celsius. The idea of the variety of conductivity and estimation of activation energy in various regions, determined from the temperature reliance of AC conductivity, recommend that the conduction process is of blended sort, for example, ionic, polaronic and space charge produced from the oxygen ion vacancies. AC impedance plots as a function of frequency at various temperatures were utilized to examine the electrical conduct of the sample. PTCR properties is seen in low temperature, equals 200 OC, locale and above, which demonstrated the negative temperature coefficient of resistance character. Complex impedance investigation focused on the relaxation phenomenon is polydisperse and non-Debye type in nature. Subject areas: condensed state physics. Keyword: ceramics, perovskite structure, solid-state reaction, X-ray diffraction, dielectric, impedance, diffuse phase transitions. 1. Introduction. Since the disclosure of barium titanate, BaTiO3, in polycrystalline structure, it has been comprehensively used in various electronic portions, for instance, multilayer capacitor, MLCs, positive temperature coefficients of resistivity, PTCR, thermistor, piezoelectric device, optoelectronic fragments and semiconductors. Morrison et al. 2001, Weber et al. 2001, Mohanty et al. 2009. For MLC's applications, dielectric materials ought to be electrically ensuring, greater than 1010 OCM and show high permittivity. Regards, 1000, at room temperature, Morrison et al. 2001. Significant properties for business contraption applications have been by and large observed at first in poisonous perovskite blends, for instance, PMN, PT, PNN, PZT, PLZT, and PZT, Park and Shrout 1997, Fu and Cohen 2000, Mohanty et al. 2009. These pieces have an obvious drawback of flightiness and hurtfulness of lead. Producers are by being avoided using materials, especially those containing lead. Along these lines, starting late, ask about undertakings have been facilitated more towards the improvement of biological pleasant without lead creations. Reprisal. The previously mentioned, the ferroelectric oxides of perovskite assistant family have fundamentally been tried for their accommodating dielectric 5, electro-optic 6, nonlinear optic 7, pyroelectric 8, piezoelectric 9 properties. A perfect perovskite structure can be addressed by a general condition as ABO3, where A will be a gigantic cation, mono to trivalent, and B is a little cation, a change metal molecule. The A particles include the edges of the 3D square, which is 12 formed, while the B particles sit on the body center situations inside an oxygen octahedron, which are at the face center positions. Literature survey unveiled that a bottomless of research has been developed on perovskite type ferroelectric oxides, neobates and tantalates 11, 12, 13. We couldn't find any. In any case, no work is executed on the assistant, Dielectric and electrical properties of flow compound. Looking to the centrality of the material, we have consolidated and examined the auxiliary and dielectric properties of another compound having the invention condition Na0.5Bi0.5Ti0.9Zr0.1O3. 2. Experimental procedure. 2.1 Material preparation. The stoichiometric ratio of starting chemicals NaCO3, 99.9%, Bi2O3, 99.9%, TO2, 99.9%, and ZrO2, 99.9%, were weighed for the composition Na0.5Bi0.5Ti0.9Zr0.1O3, x equals 0.1. The gauged powders were mixed precisely by an agate mortar for around 3H. The powders were then calcined at enhanced temperature and time, 900 degrees Celsius for 12 hours, in cool. The calcined powder along these lines acquired was mixed with PVA, polyvinyl liquor, cover, crushed, and were palletized ensuingly, around 10 mm in width and 1 to 2 mm thickness, under unioxile weight of 4 times 106 N/m2. From that point the pellets were sintered in air environment at 950 degrees Celsius for 12 hours. At last the pellets were covered with high virtue silver paint, and afterward warmed at 150 degrees Celsius for 2 hours before executing the electrical estimations. 2.2 Material characterization. X-ray diffraction, XRD, pattern of the material acquired in a tremendous scope of Bragg edge 2. 200 equals 2 equals 800, at a checking pace of 3/0/min by a X-beam diffractometer, Rigaku, mini-flex, with Cu radiation. Equals 1.5405 A, at room temperature. The surface morphology of the pellet test of the material was recorded with a high-goal scanning electron microscope, SEM, Joule JSM model, 5800F. The dielectric characterization of the example was arranged in the temperature scope of 32 degrees Celsius, 5000 degrees Celsius and frequency range of 1 kHz to 1 MHz, utilizing a PC-controlled Hioki Hydester LCR meter. 3. Results and discussion. 3.1 Structural and microstructural analysis. Figure 1 and 2 shows the crossroad pattern of the sample. Ordering of the considerable number of peaks of the sample were finished taking their 2 values by a PC program package, PADMULT14 in distinct crystal system and cell arrangement and are followed to be sharp and solo, which the peaks are discrete from those of ingredients guaranteeing the advancement of new single-stage compound. Based on the best understanding, in light of least squares refinement, between investigated, OBS, and figured, CAL, interplanar separation D, i.e., S, Dobbs, CAL, equals least, an orthorhombic unit cell was chosen with cross-section parameters, A equals 23.6720, 29, B equals 8.5031, 29, C equals 7.5427, 29. Evaluated standard deviation in enclosures, which are consistent with the announced ones 15. The soundly normal scattered crystal light size, D, of the compound was figured to be 15 nanometers utilizing Scherer's condition, D equals 0.89/SS1/2 cos.HKL, where equals 1.5405 A and SS1/2 equals peak width of the reflection at half maxima 16. The commitments of strain, instrumental mistake, and other obscure impacts in the peak widening have not been taken into board during the crystal light size list. The room temperature SEM micrograph, figure 2, left, of the NBTZ compound, affirmed homogeneously and non-uniform distribution of the grains over the whole surface of the sample. The grain size assessed from the histogram figure 2, right, is followed to be of 6.9 m true to form. The grain size of the sample acquired here is immense in contrast with the crystal light size identified from Scherer's condition. Subsequently, a performance grain has enormous number of crystal lights 17. 3.2 Dielectric analysis. The variation of dielectric parameters, relative dielectric permittivity, and loss tangent, 10, with frequency is shown in Fig. 3. Both dielectric permittivity, and loss tangent, 10, decline forcefully with the ascent in frequency, which is a general property of dielectric materials. 4,5. The estimation of dielectric constant decreases at higher frequencies, and inevitably arrives at a steady worth that might be expected to the more slow development/jumping of electrons in dielectric materials. 22. The electron jumping at high frequencies can't follow the changing electric field, thus they need to travel through grain and grain boundaries. Since the grain boundaries have high obstruction, it causes space charge polarization as the electrons pile up there, which expands dielectric constant at a lower frequency. At higher frequency, dielectric constant decays as the collection of charges at grain boundaries diminishes. The Maxwell-Wagner and Coops phenomenological models clarify such kind of dielectric conduct, i.e., in the area of lower frequency the dielectric constant decreases rapidly while at higher frequency locale it decays gradually. 23. In light of these models, the structure of the dielectric material is partitioned into two layers, i.e., the exceptionally leading grains viable at high frequency and ineffectively directing grain boundaries viable at lower frequencies. The tangent loss, 10, changes along these lines, as in that of, with frequency. The 10 is normally higher in the lower frequency locale because of higher obstruction of grain boundaries, for which more energy is required for the development of electrons. In the higher locale of frequency, the opposition is low, which demonstrates lower estimation of 10. This may be due to the dielectric relaxation phenomena occurring in the compound. 24. The temperature assortment of relative dielectric constant, ER, at some picked frequencies of compound is shown. Figure 4. The plot decidedly settled the ferro to paraelectric arrange progress at 268 degrees Celsius. The estimation of ER is little at low temperatures, which increases with rise in temperature. The dielectric constant, ER, at frequencies 10, 50, 100, 500, and 1000 kHz are viewed as 352, 225, 198, 170 and 162 individually at the transition temperature. The assortment of TAN seeks after a comparative pattern as that of ER. The extension in the estimation of TAN may be relied upon to I. Improvement in the conductivity and 2. Decline in the responsibility of ferroelectric domain. Wall 18. Quencies. 3.3. AC conductivity analysis. The AC electrical conductivity is resolved using the dielectric data and an exact association equals 0 tant, where point 0 equals permittivity of free space and equals angular frequency. Figure 5 shows the variety of as a component of temperature at frequencies 10 and 100 kHz. The idea of the variety, Figure 5, is practically straight over a wide temperature zone conforming to the Arrhenius relation, equals 0 exp, /t, 19, every one of outlines is separated into two unique regions autonomously of frequency. Each partitioned locale is portrayed by various slopes indicating distinctive activation energy. The solid line of figure shows the linear fit. The activation energy determined from the slope of the curve at various temperatures has been looked at in Table 1. In light of the dielectric phase transition, variation from the norm in conductivity was watched for the whole compound at temperatures about equivalent to its Curie temperature, which might be a result of the dielectric phase transition. The estimation of increments with increment in temperature demonstrating negative temperature coefficient of resistance, PTCR, behavior. The expansion in conductivity is because of the jumping activity of the ions in view of thermally initiated electrons. At high temperature, higher estimation of activation energy demonstrates that conductivity is for the development of oxygen vacancies. Activation energy is low at high frequency when contrasted with that at the low frequency, Table 1. This is on the grounds that at low frequencies the general conductivity is the consequence of jumping of charge carriers over a huge separation, and at higher frequencies is limited to just closest neighboring imperfection sites. 3.4 Complex Emittance Spectroscopy. Complex impedance spectroscopy procedure is a successful and basic adaptable technique to break down the frequency subordinate response of different electrical parameters and impacts, grain boundaries, and electrode impact and so forth, of the compound related to basic impedance detailing. The yield response in the contemplated sample is estimated by applying an AC signal over the sintered pellet. Fig 6 demonstrates the frequency reliance of impedance plots at the chose temperatures. The diminishing idea of the real part of impedance, Z, with the expansion in frequency and temperature can be shown in the figure. In the high frequency region, Z matches with one another to accomplish a roughly consistent worth. The total converging of the curves of Z for various temperature at high frequencies, over 100 kHz, might be because of the semiconductor properties, and arrival of space charges. The declining pattern of Z esteem uncovers the nearness of negative temperature coefficient of resistance behavior in the material. 25. Figure 7, A and B, and Figure 8 speaks to the variety of imaginary part of impedance, Z, and modulus as a component of frequency at various temperatures for Na0.5Bi0.5Ti0.9Zr0.1O3ceramic. In the lower frequency side, ordinary varieties in Z values with temperature and frequency were watched, and every one of the curves at various temperatures seemed to converge into a solitary curve in the higher frequency locale, Figure 6A and B. The decrease in Z with increment in temperature beneath 200 degrees Celsius affirms PTCR behavior of the compound, or more, that NTCR behavior is watched. The moving of the Z max in the direction of high frequency side in high temperature region is a consequence of relaxation phenomenon in the system. The reduction in resistance of grain when temperature rises is the cause of the shifting of peaks. Merging of all these curves at fusion frequency, FF, is a symptom of the gathering of space charge in the studied compounds. 21. The low frequency area peak compares to grain boundary, while higher frequency region peak speaks to the bulk, grain, commitment. Decrement in peak height of the impedance spectra with rise in temperature is a characteristic feature very familiar in polycrystalline ceramics. 22 to 24, which indicates temperature evolutions of relaxation processes. The estimation of resistance and capacitance for grain and grain boundary were gotten utilizing the relation 2PFMRC equals 1 from Z versus log F plot and showing commitments from grain and grain boundary in the samples. The figure 6 shows the plot of imaginary part M with frequency at various temperatures. The utilization of modulus spectroscopic plot is especially helpful for isolating segment with comparable resistance, however extraordinary capacitance. In figure 6, peaks give off an impression of being moved towards higher frequency side with ascent in temperature. It is additionally seen that M peaks expand with decline in temperature. The watched temperature and frequency reliance of M emerges because of conveyance of relaxation time in the sample. The expanding of M spectra must be inherently non-exponential process, as in TUM relationship among diffusion of the charged species, or assorted varieties in the microstructure of the material, driving consecutively circulation of conduction of confined charged species in space and time to react electrical impact. 3.5 Nyquist plot. The Nyquist graph, impedance range, shows the variety of the real part of impedance, Z, with its imaginary, Z. The impedance attributes of the sample demonstrate the nearness of bulk, grain boundary, and electrode interfaces impacts in the material. With an ascent in temperature, the impedance curve steadily bent to frame semicircle, appeared in embedded Fig 9, with the adjustment in their middle point to the starting point of the plot. This deviation in the pattern of the semicircular arc with variety in temperature proposes the impedance normal for the sample. In light of the investigation of the attributes of the two semicircles framed in the temperature range of 100 to 475 degrees Celsius, we can presume that the compound has both grain and grain boundary impacts in the electrical properties. The estimations of grain resistance, Rg, grain boundary resistance, RGB, grain capacitance, CG, and grain boundary capacitance, CGB, are appeared in Table 2. Fig 10. Variation of M with M at different temperature of Na0.5Bi0.5Ti0.9Zr0.1O3. 3.5 Polarization Study. The hysteresis loop of the samples polled at a field of 6 to 6.5 kV/cm for 24 hours in silicon oil bath is obtained using Precision Workstation, PE Loop Tracer, Marine India, New Delhi. Figure 11 represents the room temperature hysteresis loop of Na0.5Bi0.5Ti0.9Zr0.1O3 compound. As dielectric breakdown of the prepared ferroelectric samples occurs at a lower field, as a result, the saturation polarization could not be obtained at the experimental range of field. Therefore, we are unable to obtain a proper PE loop. Using the hysteresis loop tracer, polarization of the prepared samples of different thickness and area are measured. The anomaly obtained in dielectric plots of the prepared compounds as observed in previous section is correlated with ferro to para phase transition, which is confirmed from the nature of PE loop obtained. High leakage current and partial reversal polarization causes the unsaturated hysteresis loops noticed for all the samples under the applied field. The low value of polarization is because of lesser size of bulk size, which results of plenty of bulk interfaces. The bulk interfaces are the regime where permittivity is very low and it causes poor ferroelectricity in the materials. The polarization becomes discontinuous at the interface and surface of bulk, which results a decrease in polarization, 2pr, 28. For conclusion. The polycrystalline sample of NBTZ was set up by a solid-state reaction course. Fundamental X-ray assessment asserts the single-stage orthorhombic crystal structure at room temperature. The plot positively settled the ferro to paraelectric stage change at 268 degrees Celsius. Addition of Zr builds room temperature and peak dielectric constant values, which can be valuable for dielectric for capacitor application. The dielectric constant of the ceramics lessens with expanding frequency. Impedance and modulus spectroscopy uncovers the nearness of grain and grain boundary commitment in the sample. The activation energy of the compound was seen as particular in different regions, showing nearness of different conduction segments. Acknowledgements. Panda recognizes North Orissa University for the co-activity and help during his Ph.D. research work. He very appreciative to Director, PXE, Chandipur, for permitting him for the exploration program. The authors are grateful to Professor R.N.P. Choudhary, Professor, Department of Physics, ITHR, Bhubaneswar, who had helped us and allowed us to utilize his laboratory during synthesis of compound and some of investigation of its properties. Panda additionally recognizes Department of Physics, Betnoti College Betnoti, for enabling him to do some trial work during his examination. Conflicts of interest. The authors pronounce no irreconcilable situations with respect to the publication of this paper.